Hello, and welcome to Automated Evolution of Feature Logging Statement Levels using Good Histories and Degree of Interest. My name is Rafi Kachadorian from CUNY Hunter College and the Graduate Center. This is joint work with my collaborators Yiming Tang from Concordia University, Alan Spector from CUNY Hunter College, and Mehdi Ben-Herzadeh from Oakland University. Logging is pervasive in modern software. Big data systems typically deal with high volumes of transactions, and logging statements are found in source code, which means it's tangled and scattered across the system and in line with core functionality. However, logging is useful for many things and essential for reporting security and privacy breaches. Modern software is also feature heavy, implementing hundreds of features. And logging statements, although more informational, also capture important aspects of feature implementations. We call such logging statements feature logging statements. They are useful for validating feature implementations and diagnosing unintended interactions between other features. However, too much logging can cause information overload, which makes post-mortem analysis of logging information difficult. Understanding system behavior in production and diagnosing problems can also be challenging. Furthermore, challenging during development as logs pertaining to auxiliary features or features that are not as recent as those currently being developed are tangled with those under development. Logging statements are typically associated with a log level, which dictates whether the log should be emitted, if at all. Here we have an example of a logging statement on an object logger calling the log method and giving the finer logging level. After the log level, we have a particularly dynamic string statement outputting the system health. This log will execute, particularly giving the system health, if and only if the run level of the logger object is less than or equal to the finer level. Logging levels basically curtail log information to combat information overload. However, as software evolves, logging statement levels correlated with surrounding feature quotations may also need to be changed. Ideally, feature log levels would evolve with the system as it's being developed. Particularly, higher log levels, for example, a logging level like info, will be assigned to logs corresponding to features with more current stakeholder interest or those that have been recently edited. Likewise, lower log levels would be assigned to features that have not been recently edited or are of less interest, for example, a finest log level. Here we have our overview of the architecture of our approach for log level rejuvenation. More details of this approach are in the paper, but I'll briefly go over them here. Our approach automatically evolves feature logging statement levels by mining Git repositories to discover the interestingness of code surrounding feature logging statements. To do this, we adapt a degree of interest model from Myelin from the work of Kirsten and Murphy. Myelin is a standard Eclipse development plugin IDE. It focuses on graphical components of the IDE, so that only interesting artifacts related to the current active task, in many cases a bug, are revealed across views of the IDE. The more you interact with a particular element in the IDE, the more prominently it appears in the IDE across views. Likewise, less recently used artifacts appear less prominently. In adapting Myelin for our approach, we programmatically manipulated a DOI model using Git code changes. Then, we transformed the source code to rejuvenate feature logging statements based on these changes. The result is that we pulled those logging levels closer to the features whose implementation is working on more and more recently to the forefront, and pushed those related to features whose implementations are worked on less and less recently to the background. Our goals are as follows: to reduce information overload and support system evolution by automatically bringing more relevant features to the developer's attention and vice versa. Here is a screenshot of our implementation. We implemented our approach as an open source plugin to the Eclipse IDE called the Rejuvenate Log Level. The approach may also be used for popular build systems via plugins. It supports two popular logging frameworks, namely Self4J and Java Util Logging, JUL for short. It integrates with JGit and Mylin, and is publicly available on GitHub at the following URL. To evaluate our approach, we formed the following research questions. 1. How applicable is our tool, and how does it behave with real-world open source software? 2. Does our tool help developers focus on feature implementations that contain bugs? 3. Do developers find our results acceptable, and what is the impact of our tool? Details for our evaluation are found in our paper. However, I'll briefly overview them here. In short, we studied 18 Java projects comprising of approximately 3 million lines of code and approximately 4,000 logging statements. The approach is fully automated, and its runtime was 10.66 seconds per analyzed logging statement and 0.89 seconds per clock change. Overall, we found that developers do not typically think about how their logging statements evolve along with their source code. And our tool is able to successfully analyze 99.26% of candidate logging statements. Some of the failures were pertaining to extracting log levels, which require data flow analysis in some cases. As a side product of our approach, we found that it increased the log level distribution of the code by approximately 20%. This means that developers, by using our tool, increase the spectrum of logging levels available to them that they're utilizing. We also applied our tool to buggy code to see how it performs in buggy contexts. Particularly, we're interested to see if our tool would transform log levels higher in near buggy code and lower versus code that did not contain bugs. And we found it did this 83% of the time. We also performed a preliminary pull request study where we found that we were able to integrate our patches as a result of our tool to two large and popular open source projects. This is a rate that's comparable with some related work. Like I said, more details of the evaluation can be found in our paper. In conclusion, feature logging statements document important value and track progress of feature implementations. And as interest of these features evolve over time, feature logging levels may also require modification to combat information overload. Ideally, features that are more recently developed and more relevant to developers and other stakeholders at the time would appear higher in log levels, and vice versa. Our approach discovers and rectifies mismatches between feature interest levels and logging levels. And the results show that the technique is promising at alleviating the burden of manually developing logging levels. In the future, we'd like to expand our pull request study, as well as issue a wide-scale developer survey. Lastly, we plan on enhancing our logging statement level classification tool with heuristics for machine learning. Thank you for your time, and I will now take any questions.